Hello guys, in this video I'll give you some information about applications of determinants. Okay, let's look at minors of a matrix. Suppose that A is an n times p size matrix. The determinant of a k times k square submatrix obtained from A is called a minor of order k of the matrix. You see here, in order to get the k times k square submatrix from A, we remove n minus k rows and p minus k columns. Let's look at this exercise. Suppose we have the matrix of A. Determine one minor of A of order 1, 2, and 3. From the definition, you know that in order to obtain one of the minors order 1, we take 1 by 1 size matrix. For example, you can take this 3. A prime is 3. This is 1 times 1 size matrix. From here, we calculate its determinant. The determinant of 1 by 1 size matrix is equal to its coefficient. 3, this. Let's find one of the minors of A of order 2. Then in this case we take 2 times 2 square matrix. For example, you can take maybe this one. A2 prime. I use this notation A2 prime for 2 times 2 submatrix. 0, 1, 1, 6. Then from here its determinant will be 0, 1, 1. 6 is 0 times 6 minus 1 times 1 is minus 1. Minus 1 will be a minor of A of order 2. Let's take 3 times 3 submatrix. I will use this notation A3 prime. For example, we can take this submatrix 1, 2, 3, 1, 0, 1, 0, 1, 6. 1, 2, 3, 1, 0, 1, 0, 1, 6. Its determinant will be 1, 2, 3, 1, 0, 1, 0, 1, 6. Here I will use the expansion formula along the first column. It will be this. 1 times the determinant of 0, 1, 1, 6 minus 1 times the determinant of 2, 3, 1, 6. And here you know we have plus 0 times this minor. It will be 0, we don't write. Is equal to minus 1 minus 9 is minus 10. That's it. And minus 10 will be one of the minors of A of order 3, because we get this number from the 3 times 3 matrix. Okay, that's it. Rank of a matrix. First, I'll give you the definition of linearly independent and linearly dependent set of vectors. Okay. The set of vectors v1, v2, and so on, vn is said to be linearly independent if lambda 1, v1 plus lambda 2, v2 plus and so on plus lambda n, vn is equal to 0 vector, implies that lambda 1, lambda 2, and lambda n, all of them are 0. If we have some I from 1 to n, such that lambda I is different from 0 and lambda 1, v1 plus and so on, plus lambda I, vi plus so on, plus lambda n, vn is equal to 0 vector, then we say that the set of v1, v2, so on vn is linearly dependent. Here and here, 0e is the 0 element or 0 vector of a space from where we take these vectors v1, v2, vn. Okay, I'll give you detailed information about linearly independent and linearly dependent sets in the topic of linear spaces. Okay, let's find the value of lambda I vi from this expression. You know, lambda I vi will be 0 vector minus lambda 1 v1 minus lambda n vn. You see, 0 vector minus this one will be this one itself, minus lambda 1 v1 minus so on minus lambda n vn. From here, if we find the value of vi will be minus lambda 1 over lambda I v1 minus so on lambda n over lambda I vn. You see, in this case, we can express the vector of vi as a linear combination of v1, v2, v3, and so on vn. Because of this, instead of this definition, you can say that if one of the vectors of this set can be expressed by others, then we say that this set is linearly independent. Example. Let's take two vectors. v1 is 1, 2 and v2 is 2, 4. You know that here we can write v2 as 2 times v1. You see here we express v2 by v1. Because of this, the set of v1, v2 is linearly dependent. Okay, let's look at the example of linearly independent set. Example. Let's take the set of v1 is equal to 1, 2 and v2 is 0, 1. This. Let's write this expression for these vectors. Lambda 1 v1 plus lambda 2 v2 is 0 vector. 0 here I will write r2. Because you know that these vectors are the elements of two-dimensional space. From here, lambda 1 times 1, 2 vector plus lambda 2 times 0, 1 vector is the vector of 0, 0. Then from here, you know it will be lambda 1, 2, lambda 1 plus 0 lambda 2 is the vector of 0, 0. You know, this part will be this. Lambda 1, 2 lambda 1 plus lambda 2 is 0, 0. And also we know that if two vectors are equal, then corresponding coefficients will be the same. Lambda 1 will be 0, and 2 lambda 1 plus lambda 2 is also 0. From here, lambda 2 is also 0. This and this. You see, this equality implies that lambda 1 and lambda 2 are 0. Because of this, the set of v1, v2 will be linearly independent. Okay. Let's look at three-dimensional space R3. From the school, you know that if we take any vector from R3, then this vector will have 3 coordinates. We can write x1, x2, x3. Here x1, x2 and x3 are real numbers. And also, you know that if we take 4 vectors from 3-dimensional space, for example this, v1, v2, v3, v4 from 3-dimensional space, then we can write one of them as a linear combination of others. For example, if you take, for example, v4, you can write v4 as lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3. Because of this, the set of v1, v2, v3, v4 is linearly dependent. Let's look at the definition of a rank. Rank of a matrix is a maximum number of its linearly independent column vectors. Here we have an important theorem in order to define the rank of a matrix. Okay, the rank of an n times p size matrix A is the greatest integer R such that there exists a non-zero minor of order R extracted from A. Proposition: the rank of a matrix A and the rank of its transpose are the same. Then using this proposition, instead of this definition, we can say that the rank of a matrix is the maximum number of its linearly independent row vectors. Instead of column vectors, you can take row vectors. That's it. Let's look at this exercise. Suppose that we have a real number A. Determine the rank of the matrix A. Here, in order to determine the rank of this matrix, I will use this definition and this theorem. First, we look at the column vectors. 1, 1, 1, 1, 2, 1, 2, 3, A, 1, 1, 1. You see these vectors are the elements of 3-dimensional space. You know V1 is 1, 1, 1, V2 1, 2, 1, V3 2, 3, A, V4 1, 1, 1. These are the elements of 3-dimensional space. And also, as I said on previous slide, 4 vectors in 3-dimensional space are linearly dependent. Because of this, the rank of this matrix will be less than 4. Rank A will be less than 4. It may be 0, 1, 2, or 3. Then we use this theorem in order to define the rank of A. Then first we start from the greatest submatrix of A. For example, we can start from this one. 1, 2, 1, 2, 3, 1, 1, A, 1. This. We calculate its determinant. 1, 2, 1, 2, 3, 1, 1, A, 1. This. Here we use the expansion formula along the first column. Then the result will be this. The determinant of 3, 1, A1 minus 2 times the determinant of 2, 1, A1 plus 2, 1, 3, 1. If we calculate this expression, the result will be A minus 2. From here, if A is different from 2, then you see this minor will be different from 0. Because of this, the rank of A will be 3. Look at here. The rank of matrix A is the greatest integer R such that there exists a non-zero minor of order R extracted from A. If A is 2, then all 3 times 3 submatrices will be these ones. 1, 2, 1, 2, 3, 1, 1, 2, 1, 1, 2, 1, 1, 3, 1, 1, 2, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, and 1, 1, 2, 1, 2, 3, 1, 1, 2. This. If we calculate the determinants of these matrices, 1, 2, 1, 2, 3, 1, 1, 2, 1. You see first row and last row are the same. Because of this, this determinant will be 0. Look at this, the determinant of this. 1, 2, 1, 1, 3, 1, 1, 2, 1. You see first row and last row are the same. Because of this determinant will be 0. Look at the determinant of this. 1, 1, 1, 1, 2, 1, 1, 1, 1. This is also 0 because first row and last row are the same. This 1, 1, 2, 1, 2, 3, 1, 1, 2. This is also 0 because first row and last row are the same. This. You see, if alpha is equal to 2, then the determinants of 3 by 3 times submatrices will be 0. Then in this case, the rank of A will be less than 3. Let's check the minor of order 2. For example, let's take this one. 1, 1, 1, 2. 1, 1, 1, 2. The determinant of 1, 1, 1, 2 will be 2 minus 1 is different from 0. You see the rank of order 2 is different from 0. Because of this, the rank of A will be 2. Then the answer will be this. If A is different from 2, then rank of A will be 3. If A is 2, then rank of A will be 2. That's it. Block diagonal matrices. Definition. An n by n square matrix A is said to be block diagonal if it's a square diagonal matrix in which diagonal elements are square matrices of any size k times k, with k is less than n, and the off-diagonal elements are 0. Examples. Here the matrix of A is a block diagonal matrix. You see here diagonal elements are this submatrix and this submatrix. But B is not block diagonal matrix. Because if we take this submatrix and this submatrix as a diagonal elements, here there are non-zero elements. Proposition. The determinant of a square block diagonal matrix is a product of the determinants of its square diagonal blocks. Exercise. Determine the determinant of the matrix A. You see the matrix of A is block diagonal matrix. Then using our proposition, the determinant of A will be this. The determinant of 1, 1, 1, 2. times the determinant of 1, 3, 2, minus 1. That's it. It will be 2 minus 1 times minus 1 minus 6 is equal to minus 7. That's it. Okay guys, this was our last lesson for the determinants. See you guys. Good luck for all of you.